Hello and welcome. So in this example, next couple of examples, we're going to look at how to figure out whether a relation is transitive, if it has the transitive property, by looking at its adjacent matrix. So to check transitivity of a relation, you want to square the matrix. You can multiply it using Boolean algebra, just like before. You can also multiply using like regular numbers, regular multiplication. But let's stick with Boolean algebra for now, since we're doing that. So the relation turns out to be transitive if and only if the squared matrix has non-zero entry where the original has a zero. Okay, so the relation is transitive if and only if the squared matrix has no non-zero entry where the original has a zero. Okay, so basically, if the original has a zero to start with, right, then it also has to have a zero when you square it in order for it to have the transitive property. Okay, so let's look at example 6. Check to see if this is transitive. So we're going to square. MR squared is going to be 1, 1, 0, 1, 1, 1, 0, 1, 1, and then times itself. All right. So we're multiplying the rows match with columns. So 1 times 1 is 1, plus 1 times 1, which is 1 plus 0, 1 plus 1 plus 0. With Boolean algebra, you get 1. Next row, we get 1 plus 1 plus 0, which is 1. 0 plus 1 plus 0 is 1. 1 plus 1 plus 0 is 1. 1 plus 1 plus 1 is 1. A 0 plus 1 plus 1 is 1. And next one, we have 0 plus 1 plus 0 is 1. 0 plus 1 plus 1 is 1. And 0 plus 1 plus 1 is 1. Okay? Alright, so we look at the square matrix. We check to see there's a 0 in this place and this place. But in the square matrix, these are non-zero entries. So this breaks the condition for transitivity. So you go, this is not transitive. So for it to be transitive, wherever you had the zeros in the original matrix, these need to remain zeros in the square matrix in order for it to be transitive. If they change to ones in any of the places, then you say it's not transitive. Okay? So you can check, right? If I list the elements, if I call these A, B, C, and A, B, C, those are my elements in the set, then the relation is going to be A, B, 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 BC, and CB and CC. Okay, you can check for transitivity here. So basically you're looking for anything that breaks the chain, right? So if you pair up two, you can pair up two relations where they have the same end and beginning, then if it's transitive, then the combination, right, the composition of them is going to be in there too. So let's see, I think if we choose A, B, right, so if we pair these up, A, B, and B, C, then AC would need to be in the relation for this to be transitive, and AC is not in there, so not transitive. Okay, so you can prove this rule with the matrices that, you know, the zeros need to stick to being the zeros if you do the square multiplication. Well, when you square the matrix, it basically gives you a paths of length 2. So it kind of goes, right, the original matrix tells you that A goes to A goes to B goes to A. So those are the rules. When you square the matrix, it's kind of telling you that A goes to A and A goes to B, so A goes to B. All right, so it's basically doing what the chain rule on all possible combinations of elements in the matrix. So that's what the transitive property is checking, right? So it's checking to see that if you pair up things with each other, whether you're getting that third element to be in there. So when this changes to zeros, from zeros to ones in any of these places, then that means that they're kind of the chain is not complete. Okay, so this is not transitive. So that's kind of a hand-wavy explanation. We're not going to go through the proof. It's kind of beyond the purpose of this. We could, but it's just going to make it longer. All right, so let's look at the next example. All right, so we're looking at, let me move this down a bit. Another matrix. We want to go through all the properties. All right, so this is a matrix of a relation. We want to determine if it's reflexive, symmetric, anti-symmetric, and transitive. Okay? So reflexive means that all of the diagonal entries would be 1. In this case, we have A, B, B, C are in there. So because we don't have all the diagonals entry to be 1, it's not reflexive. So this is because not all diagonal entries are 1s. And these are the main diagonals starting top left and going bottom right. Okay? All right, let's look at symmetric. Okay, so the symmetric property happens. So you can look at a matrix if you're looking across the main diagonal and the entries across the main diagonal need to be the same. So like if AB is in here, BC is in here, so they both have to be 1s, or they both have to be 0s, or they both have to be 1s. So not symmetric because we have mismatch, right? Like for example, AB is in R, but BA is not in R. Okay. Let's look at anti-symmetric. All right, so how you check for anti-symmetry? If it's, again, across the main diagonal, if there is an entry of 1, then its opposite needs to be 0. Okay? If there's an entry of 0, you don't care. Like zeros could be across from zeros, but 1s have to be across from 0, because if it's something is in there, then across from it, its inverse cannot be there. Okay, so this one matches with the 0, good. This one matches with the 0, again, good. This one matches with the 0. So for all the 1 entries, it's symmetric. Its inverse is a 0. So this is a yes. Right? If AB is in there, BA is not. Right? So this one is CB is in the relation, but AC is not. Actually, that was CA. Right? And this one, BC is in there, but CB is not. So for all the relations that are, all the elements that are the relation, its inverse, if you switch them around, are not in the relation. So that's the definition of anti-symmetry. All right, now for transitivity, you have to find m squared. Okay, so we got to square this. So we're going to take the matrix and multiply with itself. All right. So rewrite it, copy it down. I'm going to multiply it using Boolean algebra. You can use regular algebra too. It sort of doesn't, don't care with transitivity. You can sort of multiply and give kind of the regular numbers. Basically, you're checking the zeros, right? If you have 0 entries in the original matrix, these have to stay 0 in the square matrix for it to be transitive. If they change, if they're going to turn into non-zero entries, then it's not transitive. So this one you can check fairly quickly, because if it breaks down, you can stop. But I'm going to multiply the whole thing anyway. So we have this times this is 0. This times this is 1. This times this is 1. All right, so already we can see that it's broken, right? So this one changed it to a 1, but it started as a 0. So that means it's not transitive. Okay, I'm going to complete it anyway. This times this is 1. See, that one fails too. This times this is 1. This times this is 1. This times this is 0. And this one is 1. And this one is 0. Okay, so we have a couple of entries that change from zeros. Okay, so this one changed, and this one changed. So not transitive. All right, there you go, we're done. So here we can check all the properties by looking at the matrix. This is really, really useful. You can see that you can check this by hand or with a program a lot quicker than if you have the all the coordinate points listed, all the elements of the relation listed. So this is really useful.